Right. So thank you very much for the introduction, and thank you for the organizing committee for having me here. I'm a new faculty, been a bit more than around 4 months in Tel Aviv University in the School of Chemistry in the Department of Organic Chemistry. And I want to talk to you today about designing smart polymers. And my talk would be comprised of 2 parts. And when we say smart polymer, we actually mean stimuli-responsive polymers, which are polymers that upon external stimulus can alter their molecular structure, leading to some changes in properties of the bulk of the polymers. And the first project would deal with enzymatically triggered self-assembly of blockopolymers. And it's long been known that if you take an amphiphilic blockopolymer that have a hydrophilic part and a hydrophobic part, and you put it into water, for example, these would self-assemble to give micelles or vesicles or other type of aggregates. In recent years, there have been a lot of effort to try and control this process of being able to switch it from an on-off. And the way to do it is to decorate the hydrophobic part with moieties that would make it water-soluble. And then these moieties can be either switched from an on to an off state or being cleaved off to generate the hydrophobic part and generating the amphiphilic nature of the blockopolymer, and this can then self-assemble in water to give the micelles. So if you look in the literature, there have been different approaches and different methods to do so. One is to use a thermal activation. In this example, the use of N-isopropyl acrylamide, NiPAM, is a block that upon heating change its water solubility, and you generate, when you heat it, an amphiphilic structure. People have used the photochemical, like in this example from Chris Matichevsky group. When you have a blockopolymer that have this open zwitterionic charged species that make the hydrophobic part water soluble, and then by irradiation with a visible light, you generate this pyropyrene that is hydrophobic, and the blockopolymer self-assemble. Or people have used this, for example, a dye block of lysine and glutamic acid, changing the pH, change the nature. For example, if you go to pHs higher than 10, the amines are not protonated anymore, and then this block become hydrophobic, and the whole polymer self-assemble. If you look at these different approaches, and you can see that many of the applications of these polymers of this system are considered to be biological applications or biomedical applications, then it seems that all these type of applications of activations are actually quite hard to tune to the biological environment or to relevant. And the one method that is missing is the enzymatic activation of this process. And obviously, enzymatic activation should allow us to have great control and selectivity over the process due to the nature of enzymatic reaction, and obviously also be highly suitable for biological applications. So schematically, our blockopolymer is going to look, our system is going to look like this. We're going to have a water-soluble blockopolymer when the hydrophobic part is decorated with moieties that would make it soluble and can be cleaved or altered by enzymatic reactions. Upon cleavage of these groups by an enzyme, we're going to generate an amphiphilic blockopolymer, and this should then self-assemble. So the first step in this process was to choose the right polymeric platform that we can build our system on. So to choose the right amphiphilic blockopolymer, and we chose a blockopolymer of a polyethylene glycol, PEG, connected to a 4-hydroxystyrene. And the reason for choosing 4-hydroxystyrene is that due to the phenol that have a pKa of 10 at pHs lower than 10, this phenol has the proton and is going to be hydrophobic. And further on, we can use this phenol in order to attach to it the enzymatically trigger or the function that can be cleaved later by the enzyme. To synthesize this, we start from a commercially available PEG, react it with this benzyl chloride derivative of an hydroxide-mediated polymerization initiator, an NMP initiator. and we create this, what we call a macro initiator. We then react or polymerize off it a 4-acetoxystyrene, the protected version of 4-hydroxystyrene. And you can see by varying the feed ratio of the monomer, we can get block of polymers with a different degree of polymerization of the hydrophobic block, and we manage to maintain very low polydispersities. We then deprotect, or do hydrolysis, deprotect of the acetoxy to generate the hydroxystyrene by simple hydrolysis, and we can follow it or monitor it by disappearance of the peak in the IR that corresponds to the carbonyl. We then take our amphiphilic block of polymer, the PEG and 4-hydroxystyrene, the block of polymer, and we put it into water, and we look into the DLS, and you can see that both in pH 5.5 and pH 7.4, we get a very nice structure with an average diameter of 45 nanometer, which correlates very well to the structure, to the size of the block of polymer. So we have our amphiphilic block of polymer platform, and now the idea was to introduce enzymatic moieties. Now, what I'm going to show you wasn't the first try, but was the smart or the successful one. So we chose to use this phosphate group. This phosphate group, it can be potentially cleaved by an enzyme such as acid phosphatase that works in a pH optimum of 5. And at pH at 5, this phosphate group should also be a charge, hopefully giving our styrenic backbone enough hydrophilicity to make it water soluble. To synthesize this block of polymer, we synthesize this dibenzyl phosphate 4-hydroxystyrene monomer and characterize it, and we then polymerize it starting from the PEG macro initiator to get the dibenzyl protected. And you can see that again by changing the feed ratios, we can generate block of polymers with varying the size of the 4-hydroxystyrene block. And again, we maintain very low polydispersities. We then deprotect the two benzyl group. And I must say that this deprotection step almost killed the project. Initially, we had some problem of maintaining a selectivity of deprotecting only this benzyl, the phosphate benzyl ester, and not the benzyl ether between the two blocks. But eventually, we found out that using a mixture of choline and TMS bromide, we follow it by a phosphorus NMR. You can see the peak of the phosphorus corresponding to the dibenzyl. We then, using choline and TMS bromide, generate the silyl ether in situ, and then being hydrolyzed very rapidly to the phosphate. So I've shown you. We then take our block of polymer, and go to the dynamic light scattering. We can see very low intensity of scattering, indicating that at this concentration, the polymer is water soluble and doesn't aggregate, so it exists in the form of free polymer chains. And so I've shown you so far that we can synthesize tailor-made monomer that are tailored for a specific enzyme and polymerize them to this water-soluble polymer. Now, the next key question was whether an enzyme such as acid phosphatase could recognize this phosphate group, because after all, this acid phosphatase was not its natural substrate. Let's say it's not 4-hydroxystyrene, or the phosphate, not 4-hydroxystyrene. And so the key question was whether the enzyme would be able to recognize this phosphate and cleave them. In order to do so, we did an NMR experiment taking advantage of the fact that we have the phosphorus. We have a very nice handle, and you can see here the broad peak in the phosphorus NMR that corresponds to the phosphate on the polymer. And we add the enzyme, and you can see already a bit after half an hour, and then slowly you can see an appearance of a new peak that corresponds to the free phosphate. Now, I want to notice two key issues or two key points on this slide. One is that the activation in this case is rather slow. It took 11 days to get to roughly was around 40 or 50% conversion or cleavage of the phosphate. So still, we get between 60 to 50% of the phosphate that are still on. And that's the second point, is that the cleavage seems to be incomplete, and it stopped. I kept on monitoring this reaction for more than a month, but basically after 11 days, nothing happens. So it stays stuck in this case, and I'll get back to it in a few slides. So, okay, we have our block of polymer, and the enzyme can recognize this phosphate, cleave, not all of them, but cleave some of them. And the question was whether cleaving some of them is enough to get self-assembly. Now, unfortunately, because the enzyme that we were using was not highly water-soluble, and it gave a very, for unclear reason, it gave very noisy baseline in the DLS. We had to go and look for another method in order to characterize the self-assembly, and we chose to look at the fluorescence spectrum of pyrene, which is a known way to determine critical Micelle concentration of various amphiphils. And the fluorescence spectrum of pyrene is very sensitive to the environment. You can see that if you move from a polar environment to a non-polar environment, you see a slight shift in the location of the vibrational peaks, but also more importantly, you see a very significant change between the ratio of the first and the third peak, and you can use this ratio or this change in ratio to correlate and find your critical Micelle concentration. So we took a different component of the system and put them in solution that contain a very low concentration of pyrene, and you can see in blue the solution that contains only the enzyme, and you get a certain ratio. In green, you can see the solution that contains the enzyme, our block of polymer, and you can see the ratio is slightly lower, indicating that this solution is slightly more hydrophobic. And this makes sense because our polymer, after all, have a styrenic backbone, and it could be that the pyrene is feeling this slightly more hydrophobic environment, but still the ratio is very high. And you can see that the ratio is maintained after 24 hours. There's no changes. However, if we take our polymer and add the enzyme, and you can see that already after 5 minutes, which is essentially the time it takes to take the enzyme, pipe it into the solution that contains our polymer, mix it, put it in a cuvette, and read it in the fluorimeter. It's around 5 minutes to get decent reads. You can see that there's a significant decrease in the ratio, indicating that we have formed some hydrophobic pockets or areas within our solution, and the pyrene sense it, or its fluorescence spectrum indicates so. You can see that this ratio is maintained, it stays exactly the same after 24 hours, indicating that there's no change. Whatever happened, in this case, happened very fast, within the first 5 minutes. In gray, you can look at the solution that I've shown you of the block of polymer that was synthesized chemically, the PEG-4-hydroxystyrene, and you can see that for this, the ratio is lower than the case of the enzyme, indicating again that we get incomplete cleavage. So the pockets, the hydrophobic pockets we generate here are not as hydrophobic as in this case. Now, about the rates differences between this experiment and the NMR experiment, this comes from the reason that in the NMR experiment, in order to get a decent signal, I had to use a lot of polymer. But as I told you, the enzyme wasn't very soluble, so I was limited in the amount of enzyme that I could add, and I was adding a lot of polymer, so I had the ratios that were changing the kinetics. And here I could use basically less polymer to get this, the data, and therefore it's the ratios between the polymer that determine the rate. About the incomplete cleavage, if you rethinking about these results later, you think you have this, okay, you have your polymer chain, and then the enzyme come and randomly start chopping these phosphate groups one after another. And then once it's chopped, let's say 4, 5, maybe 6, 7 groups, your polymer already become hydrophobic. It's not as hydrophilic as it was before, and then it starts to self-assemble. Once it's self-assembled, the residual phosphate are now entrapped within a hydrophobic core that is in the center of a micelle, and the enzyme cannot reach it and cleave the residual phosphate. And this also can explain the fact that our pockets are somewhat more hydrophilic, or not, somewhat more polar than in this case, because they probably have this residual phosphate that are buried inside, making it not so. Another more visualized evidence, you look at the TM result, and this in black is just the grid of the TM substrate. And you can see that we don't see anything for the case of the solution of the polymer or the acid phosphatase. However, if we mix the two of them together, we can see very clearly formation of aggregates with an average diameter of 90 nanometers. That correlates, again, or prove our concept of adding the enzyme and achieving self-assembly. So I managed to show you in this part that we could design and synthesize monomers that are tailored to a specific enzymatic activity. We wanted to get full activation. It turned out we couldn't, but apparently we don't need full activation in order to control the self-assembly or trigger it. And now we're looking into using different polymeric architectures in order to explore this field further. In the second part, I want to describe to you a different system which is already applicable. And this will deal with basically a drug delivery or a dendritic or hybrid polymer, linear dendritic block of polymer for a drug delivery application or imaging. And if we look on what a drug delivery carrier or platform needs to do in order to deliver its cargo, the first thing it needs to be able to bind the cell membrane. So the easiest way to do it is to explore the slightly negative charges on the surface of the cell, and usually by using a cationic surface on your dendrimer or dendritic carrier, you get electrostatic interaction that allows the dendrimer to bind the cell membrane. Then the dendrimers need to go into the cells through endocytosis, some kind of endocytosis, and then all these steps are as important in the process of designing or achieving delivery. Then your cargo needs to be released from the carrier in the endosome. And then the last step, and again is as important, is your drug or dyes or whatever you want to release need to be able to escape the endosome and reach the cytoplasm when it's going to do its goals. So if we look on dendrimers in the literature, there have been two approaches of using dendrimer as drug delivery platform. One is to use non-covalent encapsulation of dyes or drugs inside the cavities of the dendrimer. And the other is to bind some moieties or some drugs or dye to the outer groups, to the surface. But both approaches have their limitation. In the case of encapsulation, first, it's very hard to control the stability of these complexes. And if your stability is too strong, then your dyes wouldn't get out when they reach the target. Or if it's too low, they're going to escape before. And it's also apparent, if, again, you're looking at the literature, that usually you get a very low percentage of loading, and you work very hard to synthesize a perfectly monodispersed dendrimer. And eventually you can encapsulate inside 2.3 molecules of pyrene or dyes, which kind of takes the point of working so hard to synthesize the perfect molecules. If you look on the surface loading, again, due to the fact that many drugs are hydrophobic, and many dyes are too, we cannot decorate the whole dendrimer with hydrophobic moieties because then it's not going to be biocompatible anymore. So we're limited to decorating anywhere between 5 and 10%. Now, if you take, again, a perfectly synthesized dendrimer that you work very hard to make, and then you try to alternate or conjugate only 5%, obviously you're going to get a statistical mixture that contains everything between 0 and let's say 20% or 30%, with the average of being around 10, but again, kind of takes the point of working very hard to synthesize a monodispersed molecule if later on you're introducing a polydispersity, and also in this case we're limited by loading. So we decided to look into different architecture, and our idea was to use dendrimer where we could bind our drugs covalently to the interior of the dendrimer. This way we have the surface group free to protect our dye and also allow water solubility and interaction with the cells. And by covalently binding the drugs or dyes inside, we get two major advantages. One, we can control the stability. By controlling the bond type between our dyes and dendrimer, we can control the stability of these. And also, by pushing this reaction to completion, we can control very easily the stoichiometry of this reaction and know that each dendrimer would have the exact number of drugs on it. So to synthesize this, obviously we wanted to have a dendrimer or a dendritic carrier that is highly water-soluble, that have orthogonal functionality on the surface and the interior. We want to have high loading. And I think as important, it needs to be very easy to make. In order to achieve already some of these goals, we decided to look at a slightly different methodology for designing dendrimers or synthesizing them. And we decided to start the synthesis from a PEG core. And using a PEG core would allow us to first increase the water solubility, but the PEG also would, as I'll show you in a second, serve as a soluble support for the synthesis of the dendrimer, which makes the purification very, very simple and easy. So we start from a commercially available bis-amine, 10 kilodalton bis-amine PEG. Reaction with glycidyl propargyl ether. Each amine reacts with the opening the epoxide, generating these hydroxys that would later be used to bind the drugs. We then take our first generation dendrimer having 4 triple bonds, a reaction with photochemically initiated or catalyzed reaction with cysteamine hydrochloride, and each tile reacts twice with the triple bond. And we managed to get in 2 reactions, creating a second generation. And as our reaction conditions are orthogonal, we don't need what's very common in dendrimer synthesis when you need to do a deactivation or a deprotection or activation in each second step. Here we're creating or growing a generation in each step. So in terms of step efficiency, we're very efficient. We then do the opening, taking our G2 reaction again with glycidyl propargyl ether, generating a G3, and then taking this G3 and loading the hydroxys of the G3 with a diethylamino acyl chloride derivative of coumarin. It's going to bind to this hydroxys, and now then followed by the thiolene reaction, but this time doing it thermally, because we didn't think it was a good idea to irradiate a dendrimer with so many dyes for a long time. So we generate the structure that schematically looks like this. We have the PEG in the middle that would help us to give solubility. We have 20 internal coumarins and 32 amines on the surface. Now, each coumarin is bound for an ester bond to the dendrimer that potentially could be hydrolyzed by a hydrolytic enzyme inside the endosome. So the first thing we do is to look at the fluorescence spectrum of our dendrimer. And you can see that if we compare the fluorescence of our loaded carrier to the equivalent concentration of free coumarin, we can see that the fluorescence of our dendrimer is significantly quenched. And it kind of makes sense if you consider that you have so many dyes within such a close proximity, we get some self-quenching of the dye. We then take the dendrimer and incubate it under different conditions. So you can see both at pH 7.4 and pH 5, incubate for a couple of hours, and nothing happens. And now, again, a key experiment was to add an enzyme into the solution and see whether these dyes that are buried inside the dendrimer and are not the natural substrate of any enzyme can be recognized by an enzyme, and the enzyme can cleave them. And indeed, you can see in the addition of a porcine liver esterase that we add it, and we can see immediate increase in fluorescence, indicative that the dyes are being cleaved and released into the solution, and we're regenerating the fluorescence of the. So now that we know that our dendrimer can release its cargo upon enzymatic activation, we decided to get ready for some cell experiments. But before it, we decided to look again in our structure and take advantage of the fact that we have all these dyes that we want to deliver inside the dendrimer, but we still have all these amines on the surface, and we decided to take advantage of this orthogonality and decorate one of the amines with another dye, in this case an Alexa 647, a near-IR dye, is bound for a non-cleavable bond to the dendrimer. And this would allow us to have dual tracking. Now we can look not only on our payload, but look also on the dendrimer itself and be able to tell and this should hopefully would enable us to tell where the dye is being released and also what happens to the dendrimer after it releases its cargo. What's the fate of the dendrimer? So we have this dual tracking, and we went to some cell experiments. You can see that under this condition, the dye itself, you don't see anything because the dye by itself is not a membrane permeable at this concentration, the coumarin. You can see slightly after 30 minutes and definitely after 4 hours and 8 hours, you can see very clearly that the dendrimer go into the cells and release its cargo. If we look at the separate channels, you can see that if we look on the red, channels that correspond, again, only to the dendrimer. You can see that the dendrimer is not spread throughout the cell. It's rather localized within vesicles or certain areas inside the cell. However, if we look, there's some point of strong intensity colocalization between the two channels. However, if we look on the blue channel, which corresponds to the coumarin that's being released, you can see that the coumarin is released throughout the cell. So we now can tell that the dendrimer goes inside the cell for endocytosis. Once inside the endosomical vesicles, the dyes are being released, and then they manage to escape. And now thinking about our structure and the fact that we have a lot of tertiary amines throughout the structure of the dendrimer, our dendrimer works as a proton sponge and destabilizes the membrane of the endosomical vesicles, allowing small molecules such as the coumarin to escape the endosome and reach the cytoplasma, while the dendrimer seems to be stuck and stays too big and it's too positively charged to escape the endosome, and you're stuck there. So I've shown you that we could we managed to come up with a very, very simple and straightforward synthesis that gives us dendrimers with orthogonal surface and internal functionalities. We get high control over the stabilities and stoichiometry and degree of loading. And we can not only carry a payload into the cell and release it, but also our dendrimer act by themselves as in inducing endosomal escape and allowing the drugs to escape. At this point, I would like to thank, and there's many names on this slide, my previous supervisor in UC Santa Barbara, Professor Craig Hawker, and my wife, Dr. Elizabeth Amir, who is also a very talented chemist, and we did a postdoc together. Tyron Kang and Jenny Willis, who worked on the dendrimer project. Lorenzo Albertazzi, who was a visiting student in the Scuola Normale Superiore in Pisa, was a visiting student in Santa Barbara and did a biological, the confocal microscopy essay. Giovanni, who did some modeling of this, I haven't shown it to you today. Christopher Schul and Frauke Miller and Hans Arkan were also involved in different aspects of the dendrimer project. And last but not least, I want to thank also Ludmila and Asi, who are here in the audience, my two new students. And together we've been very busy in the last few months in establishing the lab and building it up. And we've been dealing, we're looking more and more into looking into the nanoscale of self-assembly and disassembly of polymers. But apparently not only in the nanoscale, but also in the macroscale. And this is the lab a few months before I got here. And by now we finished the disassembly part. And we're somewhere here. This was take not a few hours, but yesterday. And hopefully, now it's not going to look like this, because it looks like this, I'll have to move Shankar, the physics building, and slightly tilt the chemistry building towards a nicer view. But hopefully the lab is going to be nice and should be ready in a few months, and we could get really to work, even though both Asi and Luda have been working. We've already started generating some materials that we're looking at right now. And with this, I'd like to thank you for your attention and be very happy to answer any questions.
What about toxicity of the dendrimer once after the cargo was escaped? So I was asking about the toxicity of the dendrimers and how long does it take for them to be digested?
So right now, the dendrimers, as far as I can tell from looking at the chemical structure, are not degradable ones. They would stay. About the toxicity, we measure the toxicity, and up to 1 for this, the peg with the two dendrimers, we see roughly still 80% viability at 10 micromolar of dendrimer. So up to 1 micromolar, which is a fairly high concentration if you consider the fact that we're carrying 20 more dyes, drugs. So obviously they are toxic due to the cationic nature, but they're not very, they're not very toxic, and within the regime or range of concentration that you need to work with, they're good to work and not toxic enough. Obviously, one of the things we're going to do in Tel Aviv is introducing some biodegradability as well, so they could potentially be clear from the cells and from the body.
Okay, and I have another question. Sorry, for the enzymatically self-assembly. One of the other self-assembly motifs that you introduce, one of the big advantages is that they are reversible. So you change pH, you change temperature, and then you can flip from one side to another. Do you have any vision about how you can do that also?
Enzymatically.
Enzymatically reversible, because once you are buried inside the capsule, or then it's really hard for you to even get the enzyme there to finish the whole procedure, right? So how would you get it in to reverse it?
So first, with Enzymatic, my guess that even if, and we are working on this direction as well, of having something that's already self-assembling, for example, by using digestion of an enzyme, making it fall apart, okay, which is the reverse. So this Enzymatic could trigger disassembly. And obviously, it's more challenging, again, as these things are buried. So the first is that with the enzyme, it's going to be much more difficult, if at all, to make these things completely reversible, and that you'll be able to go both ways. So let's call them disposable self-assembly, right? It's a way of saying it can happen one time into one direction or one time into the other one. I can tell you now, based on some experience, actually with the other dendrimers that I haven't shown, but once you put all these dyes, even with all the amines, they do self-assemble. But even though they do self-assemble, we were lucky enough to get a balance of hydrophobic, hydrophilic in the structure. So they self-assemble, but they're probably dynamic enough. So you get some of the amines or some of the dyes are still exposed and accessible to enzyme. Now, once you start chipping off or getting rid of these hydrophobic dyes, then your dendrimer slowly becomes exactly the opposite. It becomes more and more hydrophilic. Once it becomes more hydrophilic, it becomes more accessible. And potentially you should be able to cleave all the hydrophobic parts. So it would be a question of balancing your hydrophobic to a hydrophilic interaction, making it hydrophobic enough to self-assemble, but at the same time hydrophilic enough so it's still a dynamic process that allows once in a while some of the groups to be cleaved. Once they start cleaving, they become more and more hydrophilic. We should be able to reach a system that works the other way around.